Hello again. I know you're really excited to be back here thinking about programming. Today's activity is really, I think it's actually easier. The coding part is easier than working out the interpolating Lagrange polynomial. I suppose this is just a second example. You might notice in this course how we're shifting from just at the beginning, we were playing around with Mathematica commands. And then the middle segment, we were learning about different kinds of variables and if-then statements and loops. And now we are trying to use all those pieces to do useful things. So today, we're going to talk about Taylor series. We've seen this several times already in this semester. And a Taylor series is simply a polynomial, and in general, it's an infinite polynomial, which approximates reasonably smooth functions. So, for example, one that we've seen in different previous classes is that cosine of x may be approximated by an alternating series of 1 minus x squared over 2 plus x to the fourth over 24. That would be minus x to the sixth divided by 6 factorial, and so on and so on and so on. So it goes on forever in that case. Sometimes the Taylor series terminates and truncates. If the original function was a polynomial, then the Taylor series you get will also be a polynomial. It'll be the same polynomial, it turns out. But in general, you should expect to get an infinite number of terms. All right. So today's activity is not just to go through a Mathematica notebook, but first I want to show you where this comes from. For those of you who have already had Calculus 2, hopefully this is a piece of cake. You can just go right to the end. But my suspicion is that if you, like most people who take Calc 2, don't really remember where things come from, especially series and sequences, and the Taylor series in particular, I suppose that must just be a topic that comes right at the end of the course, and people are moving pretty fast when they get there. So I thought it would help you out in your math class if I actually went a little bit slower and tried to motivate the definition of a Taylor series, or at least the formula for Taylor series. I'm not going to bound the error, so it's not really a mathematical proof. You'd have to work a little harder to make it into a proof, but that's okay. We're just after the essence of it. So in this video, what I want to do is kind of describe where a Taylor series comes from, and I'm going to alternate with the whiteboard to do that part. And then I'll go back and describe the formula, or sorry, the function that I want you to create. And so in this notebook, your assignment will be to write a function which calculates a Taylor series to the desired order. So, and you'll have to, as inputs, it will take the name of a function, the variable of a function, and the order of that polynomial. So that's going to be the goal. But before we get there, let's learn about what a Taylor series really is. Okay. So a Taylor series is in general, an infinite polynomial. And it turns out it's built out of the values of a function as well as all of its derivatives at a point. So the idea is, roughly, that if you know the value of a function and all of the ways that it can wiggle, all infinitely many ways that it wiggles, you can reconstruct that infinite bit of information to actually reconstruct the height of the graph at all infinite points along the real line. Now, if you're in Calc 2 currently, which most of you are, or many of you are, you know that series often have a finite or even zero-sized radius of convergence. And a Taylor series is no different. So when using a Taylor series, you really have to be a little careful and worry about convergence of the series. But in this video, we're really just trying to motivate the formula, and we're going to apply it to things where there's no issue with convergence. All right, so to derive a Taylor series, we need to remember how to integrate by parts. So I've written it down here. I didn't type the limits of integration, so you'll have to fill those in if you're following along. But integration by parts says that the integral of u dv equals uv minus the integral of v du. And in math class, you use this fact to make everything simpler. So typically, for example, if u is a polynomial of degree, say 3, then when you calculate du, you're going to end up with a polynomial of degree 2. And if you do integrate by parts again, you'll end up with a polynomial of degree 1. And if you integrate again, you'll get a constant. So integration by parts is useful sometimes for simplifying the integrand. That's not what we're going to do here. To motivate the derivation of, or to motivate the formula for a Taylor series, we're actually going to integrate by parts backwards. And by going, quote unquote, the wrong way, we will make the integrand look uglier and uglier and uglier. But the formula that pops out is nothing other than the Taylor polynomial. And if you really want to think of it, all of the really ugly stuff goes into a remainder, which becomes as small as you want by computing more and more terms. And so in practice, we can often ignore it. Okay, so I'm going to switch to the board now and go through a motivation. I won't call it a derivation, but it's a motivation. And then we can proceed. Okay. All right, here we go. So in this video, we're going to go through Taylor series. We're going to motivate. Oh, I need a marker that works. We're going to motivate a Taylor series. Okay. And the thing that keeps this from being a proof is I'm not going to worry about bounding the error and worry about convergence. We're going to work with nice lumpy functions. And so we just assume that it more or less works. And there are pathological examples. There are examples of nice lumpy functions for which this doesn't work, but they're not going to be things that we worry about. And you won't worry about them in your math class either, for the most part. There might be a few examples. Okay, so the starting point for a Taylor series is to make two observations. Let's kind of write them up here. First off, integration by parts. The integral from A to B of u dv equals uv evaluated between a and b minus the integral from a to b of v du. That really just comes from the product rule for derivatives and then integrating that. Okay, so hopefully that is a familiar formula to you. I'm going to make another observation. Another observation is that the change in a function simply equals the integral, say, the change in going from A to B. That's the integral from A to B of the derivative, I'm going to write that as f prime, of s ds. So the idea here is, well, it's a fundamental theorem of integral calculus, that the integral of a derivative simply evaluates the difference in the differentiated function, and it's the difference evaluated between the limits of integration. Notice, s is a dummy variable. That doesn't mean it's stupid, although since it's s, maybe it is. What it means is that you're going to sum over all the values of s, so there's no reason to think of it as having any particular value, because you're going to hit all the values. And in particular, s is completely independent of any other parameters that might be appearing in the problem. Parameters such as a or b. Okay, s is a dummy variable. You could call it whatever you want, but we'll call it s here. And the last thing I want to show to you to think about, though, is if s is the variable we're integrating over, when you calculate ds, in a physics context, I would say ds represents a baby step. A baby step in s is, say, yay big. If I were to add a constant to s and then take ds, take a differential of s plus the constant, then in fact it doesn't change. So what I'm really mumbling about is that d of s plus a constant in fact is just the same as ds. So that's kind of a neat observation. And to motivate the Taylor series, we're basically going to shift the constant in the differential by, we're going to shift the dummy variable by a constant just the right way, and out will pop Taylor series. Okay. Now, remember those things. Now, the formula for Taylor series is a little bit complicated. So what I'm actually going to do is write the formula down first, and then we're going to motivate it, or / partially kind of derive it. And then by having the answer written on the board, we'll know it when we see it pop out of the later calculation. So the formula is going to be that if you have a function, f of x, and it's a reasonably smooth function, then you can approximate the value of the function at x by the value of the function and all of its derivatives at a neighboring point. So I'll write the formula down and I'll kind of describe how to think of this. So let's imagine I want to know the value of the function at x, but let's say I know the function at a point called a. So I'll say, and the series will be f of x equals f of a. Think of that as the 0th derivative evaluated at a, plus f prime evaluated at a, divided by 1 factorial, which really is just a 1, so I won't even bother, I won't clutter the formula with that, times x minus a plus 1 over 2 factorial f double prime evaluated at a times x minus a squared plus f triple prime at a over 3 factorial times x minus a cubed. I'll do one last term and then you'll see the pattern. F quadruple prime evaluated at a over 4 factorial times x minus a to the 4th plus dot, dot, dot. It goes on forever in general. Okay, so that's the formula. It can be written nice and succinctly as f of x equals the sum from I equals 0 to infinity. So you start at 0, and then you work out the ith derivative. So I'm going to write that as dif dx. Evaluated, you don't evaluate it at x, you evaluate it at a. And then I need to divide by 1. So I divide by I factorial. So that's the coefficient. And then I multiply by x minus a to the ith power. So notice, how do you interpret this? When I is 0, that gives 0 factorial. That's defined to be 1. And then you take the 0th derivative. Well, that's interpreted to mean just the function itself. And so what we have here is the value of the function at x is built out of the infinite tower of derivatives plus the actual value of the function at the neighboring point a. Oh, okay, so let's think about what that means. So the idea is, first let's start with a random lumpy function. Okay, some random lumpy function. And let's say that this is x. And right here would be f of x. And let's say that this point is a. So what we are doing is we are taking the information of the function at a and the first derivative at a and the second derivative at a and the third derivative at a and all of the derivatives of a in general at a in general, and you put those together. And what they do is you use the curvature and the way those derivatives are bending to tweak coefficients of polynomials. And quite literally what you're doing is taking polynomials and wrapping them along the curve. So by adjusting the coefficients of the polynomials to match this formula, these coefficients, what they are doing for you is wrapping polynomials around the curve. So the first term, let's go back here, the 0th term would give you just a constant because you had I equals 0. This would be a constant. So the first term builds up a constant. And then the next term builds up the effect of any slope. Well, the point I chose at a actually has no slope. So that second term would evaluate to 0. But the third term in the series, which should be I equals 2, is going to build up a parabola. And if you look at this function, the second derivative of this function is negative because it's concave down. So this is going to say that what this series is telling me is I should start with a constant, and then on top of that, I should mix in a parabola that's concave down. So that has the effect of wrapping a parabola now. And then the next term is going to start to mix in a cubic polynomial. So now it's going to start to have a bit of a parabola, and it's going to start to curve over. And by adding more and more and more polynomials, you can wrap the Taylor series, kind of wraps polynomials around the original function. And if you go through more and more terms in that series, then you get a better and better approximation. So that's the idea of what a Taylor series does. Let's go through the derivation / it's really just a motivation, but it gets to the answer that we want. To do this, I'm going to start with, I'm going to note that f of x minus f of a equals the integral from a to x of f prime as a function of s ds. That's my first observation. Then I'm actually going to shift the differential like I said I would. I'm going to shift it to s, from s, which is going to become s minus a. So I'm going to rewrite this as s minus a. I'm just going to shift it by a constant. Remember, a is independent of s. It's just a constant from the point of view of doing this integral. And then we're going to integrate by parts. It's going to be a little bit cluttered, but the final bit is going to match our formula. I think I'll probably just work out the first maybe 2 or 3 terms, and then you get the idea. Okay. So we're going to integrate this by parts. So I'm going to write this. So first of all, I'm going to define or match up. I'm going to say this is u, and I'm going to say that this is v. So I integrate by parts, and I'm going to say this is going to be f prime of s times s minus a evaluated between a and x. I think I might have fouled it up. Did I mess things up? If I plug in upper limit, lower limit, I did foul things up. You know what I need to do? I need to shift it not by a, I need to shift it by x. You might say that looks really weird, but remember that x is just a parameter in this problem. So you can think of it as just being a constant here. Later on, after doing the calculus, you can allow that parameter to change, but from the point of view of doing the s integral, it doesn't matter. Very good. So this is what we want, minus the integral of, okay. So I'm going to get v. So I'm going to get v, and I'm going to get, so v is going to be s minus x. And then I get du. But I can write du as the same as f double prime ds. which I will promptly reorder. Write it as f double prime s times s minus x dx, sorry, ds. Okay. Now, this term, look what it gives me. At the upper limit, this factor gives 0. At the lower limit, it gives me a minus x. Okay, a minus x. But that's the lower limit, so I end up with a double negative. So this is going to give me 0 minus f prime at a times a minus x minus, and I'm going to, and then I have to work with this integral. Whew. Well, tell you what, let's make this thing be dv, and now to do this, let's make this equal to u. So notice what happened. We started with just a differential. We integrated by parts backwards, as it were, and now we have something which is linear. Then we're going to integrate. We'll do it again. After we integrate, we'll get something quadratic, and then so it keeps growing higher and higher orders when we do this. So I'm going to minus. Now I have to write this whole integral. This whole integral is going to be, so it's going to be u. This is integrated between a and x times v. Well, dv is s minus x. V is going to be s minus x squared over 2, evaluated between a and x, minus the integral from a to x. If you think about it, you're going to get x squared over 2 times f triple prime ds, or f 1, 2, 3 s minus x. I can't write today. S minus x cubed, squared over 2 ds. Whoa, that looks god awful. So let's clean it up a little bit. Let's pull this minus sign in to here, and this is going to become f prime of a times x minus a. I just reversed the order. Now, this minus sign, so is going to need to be distributed in, but look what happens here. At the upper limit, when I plug in s equals x, this gives 0. So only the lower limit contributes. So it will come with, so this, the part of this that contributes has a minus sign because of the lower limit, but you have to multiply by a minus sign. So they cancel out, and you get plus f double prime, evaluate the lower limit, over 2, and 2 is the same as 2 factorial, times a minus x squared. Well, since I had x minus a, then I want to write it the same way, and then that's okay. I can reorder these because of the squared nature for free. Okay, so look what happened. The difference in the function can be written as the first derivative times a linear thing, plus the second derivative times a quadratic thing. We can keep going. I'm kind of running out of steam already. I thought I had one more round in me, but I don't. So you just keep turning the crank, really. It's the same thing. And the next order, you're going to get a triple derivative popping out, and then a fourth derivative popping out, and the polynomial grows as well. So this, in fact, if I rearrange it and regroup this and write it as f of x equals f of a, this would give me f of x equals f of a plus f of a prime. Oh, handwriting's terrible today. F prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus dot dot dot. And just to show you I'm not making it all up, notice here, if you look at, this is the previous board that we had, this is f of x equals f of a plus f prime of a times x minus a plus the second derivative divided by 2 factorial times x minus a squared, and you can just keep going. It'll go on and on and on forever. Very good. Okay, so that's where Taylor series come from. Hopefully that little discussion will be helpful when you take Calc 2. Right at the very end of the course, you do this kind of stuff. All right, I want to switch back to the Mathematica notebook and go over your next assignment, which is based upon constructing a Taylor series for an arbitrary function. Okay, so we're back to the Mathematica notebook. So I showed you where Taylor series come from. And here I've kind of tried to write it all up a little bit in Mathematica. It's a little tedious to type it all in. Here's the series form of things. And then notice for some reason, when I made the notebook, I used lowercase n as my summation index, whereas on the board, I wrote down the series with an I as an index. Okay, so the goal is to create a function that where the user will input the name of a function, like sine or cosine or tangent or logarithm. And our function will be called Taylor with a lowercase t. So we will have Taylor with a lowercase c or t. And just so you kind of see what I'm imagining, I'm imagining that you use the function as follows. You'd say something like Taylor of sine, comma, and then specify the variable that you want the Taylor series to be a polynomial in. Usually we'll take it to be x. And the point about which you want to expand. Usually we call it a. So you can construct a Taylor series about any point a. The closer x is to a, the more accurate the series will typically be. But really, you can use any point. And then the last little thing, which means that our Taylor series function doesn't truly calculate the Taylor series, because a Taylor series would require an infinite number of terms, and we are only going to calculate the first of them. So I think I called that number n max. Okay, so that's how I imagine you using your function. You're going to type in Taylor, going to give the name of the function to be expanded, the place, the variable of your polynomial, the place about which you are expanding your function, and then the maximum number of terms to include. I went ahead and tried to help you out by laying out a simple algorithm that would do this. It's very similar to the kind of thing you were doing in the Lagrange polynomial class, where when you wanted, after you finding the basis functions, you pulled them all together in a sum. And this is really the same basic thing. So if you're stuck here, but you got that one to work, take a look at the other program, and you probably can just see how to modify the Lagrange function in the interpolation notebook to make this work. Okay, so we're going to need an input, which is going to be the name of the function, an input to represent the polynomial variable name, a variable in max for the highest degree polynomial, and finally a variable a labeling the point about which we are expanding. You need to create a local variable just to record the, if you want, kind of the partial sum that you get after each iteration in a loop. You want to initialize the sum variable to be 0. Before you start adding anything, you better start at 0. And then you want to use a do loop to iterate from 0. That's a little bit of a wrinkle. Highlight that there. We start at 0 because the Taylor series formula starts at 0. And then you go up to some in max, some maximum number of terms. And at each iteration, you update the sum, by this term, by this factor. Okay, so at each order, you add a term to the series, to the sum, which is 1 over n factorial times the nth derivative evaluated at a times the polynomial piece. In this project, you can use the D command to, I guess this isn't a project, I misspoke. In this homework, we'll call it, you're going to use the D command to do the derivatives, so you don't have to worry about that part. Just a little hint, kind of like when we had to graph some of the functions with the derivative, you want to take the derivative with respect to the function evaluated at some parameter, and I called it xx. And then after taking the derivative, use a rule to replace xx with a. The problem you have is that if you say that a is the number 1, then it doesn't know how to do calculus with the number 1. And so in reality, you should do calculus first and then evaluate if you want, do the derivatives first and then think of the rule as kind of applying a limit. You can almost think of it that way. So that would be my recommendation. So what I'm suggesting is you would want to say something like, for example, something like this. You might want to say d of f of xx with respect to xx, and that'll give you whatever it gives you. And after you're done with that, you might want to then use a rule to say replace everywhere you have xx, replace it with a. Okay, that would be the idea. And notice that's what it gives you in the end. So in your Taylor series formula here, I would suggest working out the nth derivative in that same way. You might want to use the Mathematica help file if you don't remember how to work out the nth derivative, or you can look back in some of the earlier files from the first third of the course where we did that. Okay, so that's the algorithm basically. So after updating the variable sum, you want to leave the loop, and before you exit the module, you want to evaluate sum one last time so that it returns the final result to the rest of the notebook. Okay, so accompanying this little function that you're supposed to write, I just thought you could play around and use your function and apply it to sine of x near a equals 0. Keep the first 4 non-zero terms. And you can test it to see how accurate your series is. It turns out it's very, very accurate in this case. Do the same thing for cosine. And then just for fun, I suggested that the third part of which is to calculate, use the same Taylor series formula and use it on a complex exponential. So this is e raised to the ix. So just in case you're worried about how to type that in, you can also do capital E raised to the power capital IX. It amounts to the same thing. Mathematica will convert it to these funny symbols. So if you don't remember how to type in the funny E and the funny I, you can use just the capital letters and it will get you to where you want to be. So it just turns out these aren't just random things. These first two are somehow related to the third one. And there's a hint, it's related to the famous Euler formula. Okay, so that is your next homework after interpolations. And this will be due on April 1st. I know it's the first day of spring break, but I'm giving this to you multiple weeks in advance. So you should be able to get this done. No problem. I know you just can't hardly wait to get started on all this stuff. Okay. Hope you guys are well. Stay healthy. Wash your hands. Make good choices. Okay. Thank you.